orbifold can be represented by a Lie groupoid. But there can be different Lie groupoids representing the same orbifold, and there is a notion of equivalence, but I'm not going to go into that. Okay. Okay. If for any x in X there exist charts U tilde G phi around X, and okay, so let me say here that with underlying map F from X to Y. So those are the underlying topological spaces, and you have a map. So of course, first of all, I should say, well, sorry about this mess, F is continuous, and for any x in X, there is a chart, and you have another chart around Y, which is F of X, such that F maps phi of U tilde into psi of V tilde. So nothing there so far. Okay? And this is the condition, and F has a CK lift F tilde from U tilde to V tilde, such that so this just means that F is a lift. So F tilde is a lift. So there is a local lifting. Okay. So this is one notion of having a CK map. So you can see that there are no condition on the groups. No homomorphism is.
No equivariant, no nothing.
Well, I mean, this of course is that it? Yeah, nothing. Because I don't have a homomorphism, equivariance doesn't make sense. Only thing is, you see, different, I mean, they project nicely. Okay. Okay, so there is another notion where we do have equivariance. Okay. Now, here, a diffeomorphism. So when I say diffeomorphism, I don't need equivariance. Okay. So a diffeomorphism F is a C infinity map with C infinity inverse. Okay, so no equivariance is needed. Now, okay, there is a stronger notion of strong map or good map. Okay, where where we require a group group homomorphisms from how should I call it, say tau from G to H, and require F tilde to be tau equivariant. Okay. Now this is.
For example, if we consider the cone with CP singularity and another cone with GQ singularity, if P and Q are relative prime, then is there a map between two of them?
Yeah, so if you want to say if there is a strong map, right, if there is a strong map.
There is no strong map.
Well, the only homomorphism we could have would be trivial, then we have to check. I'm not sure, but you can check. Okay. I mean, there would be some maps, right? But would there be a kind of a nicer map? I mean, of course, there is a constant map, right? But whether you have something better, I don't know.
So you mean that there is no relation between two local groups?
Well, one thing you can say is that in this strong sense, there is no diffeomorphism. That is obvious. If there are other maps that you have to actually study carefully.
The strong maps preserves the local groups, right?
Yeah, I mean in that sense, but strong diffeomorphisms would preserve local groups. Okay, this is, because of lack of time, I'm not going to go into this, but this is compatible with something called homomorphism of groupoids. This strong map business. Okay. So homomorphism of groupoid again would be like you have two groupoids, you have two maps from G0 to H0 and from G1 to H1, and some compatibility, natural compatibility conditions, mirroring this idea. Okay, now I want to introduce vector bundles on orbifold. Okay, so So there are again two notions. One is, of course, you can have vector bundles on topological space X okay. And this is a notation. Underlying space. And number two is a so-called orbifold vector bundles. Orbi bundle or orbifold vector bundle. on X. Okay. Okay, so let's look at this second type of object. So one thing I can do is I can describe it in terms of local charts. So locally you have this U tilde, and you'll have a vector bundle on U tilde, and then I can say this vector bundle would come equipped with a G action. Okay, and then I can say how to glue them together. So maybe I do that first, and then, well,
That's second one.
that's the second one. So
First one is just
first one is what we all know, usual. Second one. Now the second one has two descriptions, one in terms of this local charts, another in terms of groupoid. The groupoid one is kind of nicer philosophically, but let me see if okay.
maybe more abstract.
Yeah, slightly more abstract, but I meant to do it. Let's see. Okay. So an orbibundle on
H를 우리가 그 디텍트를 해내야 돼.
a G U, I don't know, vector bundle on each U tilde. Okay, so my charts are for chart U tilde, I will write GU VU. Okay, just to be.
vector bundle is equivalent vector bundle?
Yeah, it's just a vector bundle with the G action that is linear from one fiber to another, and because it is invertible, then it's an isomorphism. So what this means is if you have let's call this EU, right? Let's drop this U's, okay? That will make life easy. Okay, so if you have an element Y, then this EX goes to EY. Right, there is some isomorphism. Which we can call G star or by G, it doesn't matter, okay? Right? So some vector bundle with G action. And some gluing condition, okay? And gluing condition okay, so for any injection, so assume each EU over U tilde, E over U tilde is trivial. right? You can choose such small charts, right? Then, for any injection, U prime tilde we have the continuous map GI from U tilde prime to automorphism. Let us say that these vector bundles are complex, okay, or doesn't matter, or K equal to rank. Okay. Okay. So for every injection, it tells you how these fibers are being identified, right? Such that giving embedding U tilde prime cross CK into U tilde cross CK by x comma v goes to I tilde x comma gi of x times v. Okay, and you need such that you need composition law Gj of I for two injections at x. This is Gj of Ix compose Gi of x. Okay, so this is kind of well, I mean, if I want to describe it in this way. Now, let me see. Okay, let me take maybe 5 minutes to describe it in terms of groupoid. Okay, that would be kind of nice. So 2 in groupoid language. So first you see over here you have some group action on E, right? So first I have to define what is a groupoid action. Okay. And okay. Let G be an orbifold groupoid. That would roughly mean that these stabilizers, the isotropic groups Gx that I defined, arrows going from x to x, those are finite. That's roughly the thing. A left G space E is a manifold E equipped with an action of G. Okay, an action of is given by two maps pi. So you think that you think of this vector bundle picture, then it's kind of clear. So from the total space you have of the vector bundle, you have a map, projection map to U tilde, right? That would be replaced by G naught. Okay, U tilde plays the role of G naught. So U tildes are those. Remember that when I constructed groupoid out of orbifold, G naught was the disjoint union of the U tildes. And so this is anchor. And action, this is the map mu from the following: G1 cross E. So action is an arrow will act on elements of E, right? But you have the source target conditions, right? This condition says that this source of the arrow should match with the projection to E. Okay. Mu G comma E is defined if, of course, you see G is an arrow from point in G naught, right? If source of G equal to pi of E. Yeah.
What is orbifold groupoid?
That's what I said. Not all groupoids give you orbifolds, but very roughly speaking, all the isotropic groups Gx should be finite. Okay? There are more conditions. I mean, the actual conditions are like the source map and the target map. Those are between topological spaces, so G0 and G1, right? Source goes from arrow space to object space. The source and target has to be local diffeomorphisms. That's one of the conditions. So I'm going into those technicalities, right? Okay.
Orbifold groupoid is just you consider orbifold as a Lie groupoid. Is that different?
But no, there is a technical definition saying that which groupoids correspond to orbifolds. There is a theorem that says that certain groupoids, Lie groupoids, would correspond to orbifolds. So that's what I mean, but you can just think of it as orbifold, look at it as groupoid. Okay? Now, this is how the action would be, right? Okay? This is mu GE, has to satisfy so this is very, very modeled on this local picture. Here, basically for a vector bundle, you have an arrow, action of G on the base manifold that you have to lift. That's the same kind of thing that your G is an arrow on the base manifold, G naught. Lift it. That's all that's going on. Okay? has to satisfy the following: pi of GE. So what should this be? If you draw a diagram, this would be immediate. E goes to somewhere else. Let's see. Target of G. Right. 1x of E should be E. And G dot H dot E should be G dot H of E. So natural. Okay, so this is a general G space. Now what is a G vector bundle? You just impose the condition that this action has to be fiber-wise. First of all, E has to be a vector bundle, and this action that I define like this has to be fiber-wise linear. Okay. So here is the definition. An orbifold vector bundle on G is a G space E for which pi E to G naught is a vector bundle, and the action of G is fiber-wise linear, that is, for any G from X to Y in G1, we have an induced linear isomorphism pi inverse X to pi inverse Y. Right? Those are things that we usually write EX. And that also we call it G. Okay, so without. Okay, now all this is nice in the sense that, okay, so for two things you note. Okay, first is the following. An orbifold vector bundle is basically a vector bundle on G naught with some action, right? So let me translate this for this effective orbifolds. So note that out of all this we get an orbibundle on, and this has a name again, I didn't write, on an effective, I will just use effective orbifold let's use this notation. Right? So effective orbifold you can write as a G acting, Lie group acting on M is just a G vector bundle on M. Okay? And so this pretty much tells you how to define K-theory. Okay. Now, the other point to note is that if you have, so Ex is a Gx representation. Right? The quotient Ex mod Gx may not be, of course, may not be vector space. So if you, instead of this topological vector bundles, these orbibundles, if you look at the quotient, if you look from U tilde instead of U tilde, you look what you get on U, right? So what I mean is you have E on U tilde and you quotient it to get something, I don't know, say, and this may not have vector space fibers, but fibers in general would be quotient of vector spaces. So this look different if you look at the underlying space. Okay. Now I want to define differential forms.
So when you say Ex is better than you using E as an orbifold and it's underlying space.
Yeah. So this is always underlying space. So whenever you quotient, yeah, you view E as an orbifold. Okay. So, okay.
Excuse me, how did you look up orbifold as a groupoid? I think there are two groupoid, one is a Lie groupoid, and another is a action groupoid. They are same things?
So the action groupoid is a special kind of Lie groupoid. The action groupoid can be defined in general, like with any set and any group acting on a set. But if you want the set to be a smooth manifold and the group to be a Lie group and the action is nice enough, then it becomes a Lie groupoid. So, but in general, if you have M is smooth, G is acting smoothly on M, and so on, then the action groupoid would be an example of a Lie groupoid. So, yeah, we have two constructions, right? One coming from this very complicated general thing, and the one coming from the frame bundle for effective ones. Those are going to be equivalent. They need not be equal, but equivalent, but I'm not going into that. Right? That is a more technical things need to be covered for that. Okay. So differential forms. Okay. So I'll just write things as a groupoid. So G is a Lie groupoid,
실제로
and then I have this G naught is a orbifold. You have differential forms such that S star omega equal to T star omega. Okay. So this is kind of abstract. ST, of course, are the source and target maps from G1 to G0. So what does that mean actually? Why am I writing it like this? The idea is that you have to take invariant forms. Now and this idea you want to generalize to groupoids. And why do I write it like this? As I said, for an orbifold, this S and T, ST local diffeomorphisms from G1 to G0 for orbifolds. So, this when you translate, if you think of S and T as diffeomorphism, you can write kind of these arrows as S inverse T or something. And then it just means that you have a diffeomorphism and pullback of the differential form is itself. So if you have M mod G, this is what it means. G acting on a manifold M. In the simpler situation, this means that the omega is G invariant. Okay, if G is G on M, then above means omega is G invariant. Then you know how to
Omega G, did you say omega G is a smooth manifold?
G naught is a smooth manifold.
But that's the underlying, that's the orbifold, right?
No, so
I mean the space.
G naught is like the U tildes.
G naught is like the U tilde. Oh, right.
Yeah, right.
G naught is the U tilde, right?
Yeah. So locally, what you have is omega in omega p U tilde.
So you only consider local forms, right? Locally defined forms.
That's one way you can go from locally defined forms. Yeah, so now of course yeah. If you think of G naught as the disjoint union of,
Locally
then this is,
G invariant.
yeah,
Locally G
so
invariant.
I'm kind of maybe looking at global sections, so sort of maybe my notation is bad, but the idea, I guess, is okay. So, yeah, right, and omega is G invariant. So those are the things, okay? Now, you can define, you see, D and the pullback under any map, right? D and delta commute, right? Delta means if you have any F from map, and delta F is pullback on forms. Right, so we know that this commute. So I can induce a D on the invariant forms, right? Delta is the pullback operation on forms.
Oh,
The D and delta commute, so D is well defined.
okay, that's good.
On omega p. Okay. All right. So, okay. So de Rham cohomology is defined. So, de Rham cohomology is defined for, okay, and what you can say, this is a theorem of Satake. So he first defined this effective orbifolds. Okay. For effective orbifold, say X, H star de Rham of X equals H star singular cohomology of quotient space. Okay. A general proof. Well, I forgot the reference. If I remember, so reference. You can look at this book that you are carrying. So whatever I am doing here, actually, I mean, more or less is covered in that book. Okay. Let me just define, so integration and Poincare duality. And then I go to some, so that would kind of probably end the basic stuff. And I can go to, okay.